Okay, great. So it's a pleasure to be here. It's actually the first time that I managed to attend, so I'm very excited, and I've been learning a lot already and very much enjoying this meeting, so thank you for inviting me. So I will be telling you about the black hole. Is it too loud? About the black hole galaxy connection, and I will show you results from both the observation side and simulations, and at Redshift 0 and going out to Redshift 1. So first of all, just a motivation slide. So why do we think there is a connection between supermassive black holes and galaxies? Well, so for one thing, we heard a very nice talk just before about the M-sigma relation, which is the relationship between the black hole mass and the velocity dispersion in galaxies. And this is often interpreted as a signature, or at least a hint, that somehow the black holes and host galaxies know about each other, given the tightness of this relation. Another argument which suggests that there's perhaps a physical connection is if we look at the global ensemble, so the growth history. So the growth history of galaxies, in terms of their stellar content, was peaking at Redshift 2 or so, followed by a very sharp decline in the star formation history. And similarly, if we take all the galaxies, and if we look at the growth history of all black holes, it's a very similar shape with an increased activity and a peak around similar redshift of 2, and then a decline. So this is not telling us that each galaxy and each black hole are growing together, but it is telling us that on average, in terms of populations, galaxies and black holes are assembling their mass and growing together on average as populations. And then the last argument that is often used to infer the physical connection between black holes and galaxies is this need for the so-called Aegean feedback, so the energy coming from the black hole activity to control or shut down star formation in galaxies. Okay, so during this talk, I will often show you where are the black holes in what I call the galaxy evolution context, but as shown by this relationship between star formation rate and stellar mass in galaxies. So what you see here on the left-hand side is the so-called, what I'll call it the star forming sequence, where it is a correlation between the rate at which galaxies are forming stars and their stellar mass. And then is this other population of quenched galaxies. So at a given mass, they form much fewer stars. So this correlation is known to exist at a whole range of redshift. And in fact, the normalization changes with redshift in the sense that, so this is the ratio of star formation rate versus mass, or specific star formation rate. So the normalization of this sequence rises as we go back in time, so at higher redshift. And then besides the sequence, we're trying to understand why are some galaxies boosted up in what we call the starburst region with excess star formation, and why some galaxies are falling out of the sequence, going in this quench region, and then perhaps either slow or fast quenching, but we think there must be some fast quenching because there's often kind of a gap here. Okay, so this is relevant because if Aegean are doing the trick, then perhaps we should find them located in this region here. So what have we seen so far? I would say that there's not a real census and that the connection might still be unclear because we have a number of studies that are coming with different conclusions. So for example, it's been claimed that active galactic nuclei mostly live in the green valley between the star-forming and the quenched galaxies, or no, they instead live mostly in star-forming galaxies, or it's not really the star formation that counts, it's the mass, so they live in massive galaxies. And then we also have results that suggesting that galaxy mergers are needed to power the Aegean, or at least the most luminous Aegean. And the studies that say no, they don't live in mergers at all. So we have all these different results, but of course now I'm glossing over details. They're not the same sample selection. They're not necessarily all the same redshift in this case here. But I want to make the case that even at redshift 0, we don't even have a clear answer of this. So because of this, the idea now is to revisit this connection again at low redshift, which is what I'm going to show you next. And then I'll show you again out to redshift 1. So at low redshift, we've been using the SDSS to take advantage of the very great statistical power. So what I'll show you is galaxies that are identified on the basis of their emission lines. So several of you might be familiar already, but I'll just go very quickly. These are emission line dynastic diagram, and the purpose of using these line ratios is that the lines are excited with different energy level. So if there's a black hole versus only stellar processes, we're going to get a different intensity ratio of these lines. So what happens here is on the right-hand side is the BPT diagram. So it's O3 over H beta versus N2 over H alpha. There's two very clear branches. So there's a star-forming branch in the lower left, and the Aegean branch that goes separately here in the upper right. And then this other diagnostic is also nice to use in combination. So here the only difference is a sulfur 2 line over H alpha, because this separates between Seyfert type of Aegean, which have a high accretion rate, and liner type of Aegean, which have a lower accretion rate onto their black holes. And also liners might be contaminated with other galaxies, but I won't get into the details of that. So what I will show you next is a work from last year, 2015. What happens if we look at the star formation rate versus stellar mass plane for star-forming galaxies here in blue, these composite Aegean, which are actually in green in this plot, so they're kind of a hybrid population with Aegean activity and star formation activity blended together. They reside here. And then Seyfert and liner type. So what you can see here is that the answer to the question, where are the Aegean, will vary slightly according to which flavor of Aegean, first of all. Although, commonly, we can also notice that in all cases, they're always slightly below this sequence. So this is a sequence of star-forming galaxies, and all Aegean subpopulations are, on average, a bit below. So the author said maybe this is a hint that somehow the Aegean have something to do with the quenching as to why galaxies stop forming stars and they will migrate down from the sequence. But what I want to say next is that I think there's another parameter that's even more interesting than these Aegean flavors, and it's the Aegean luminosity. So the Aegean luminosity is a proxy of the accretion rate in terms of how many solar masses per year are the black holes accreting. And why is that potentially very interesting? It could be because we might expect, if the Aegean are really doing the quenching, that the most luminous Aegean would output the most energy into the host galaxy, and therefore be able to make a bigger difference on the star formation activity. So what do we find if we look at the Aegean in different bins of these accretion rates or luminosities? So this is again the star formation rate versus stellar mass of the host galaxies. The black contours is all galaxies. And now these red contours with the gray shaded area are Aegean populations in 4 different luminosity bins. So the most luminous Aegean here on the left, and less and less and less luminous toward the right-hand side. So what you can see is a very clear difference. At least the most notable is that the most luminous Aegean are basically on but above the main sequence. So meaning that the most luminous Aegean, which are the ones we think maybe could quench galaxies, are not quenching anything at all. They're like in the most strongly star-forming galaxies right now. And then if you look at what's going on here, is the galaxies with low star formation rates, the lowest star formation rate of all, they're like quiescent galaxies. They can only power low luminosity Aegean, if anything at all. We cannot, unfortunately, draw too strong conclusions from the lack of Aegean here, because these are actually very hard to identify due to dilution of the signal for those weak Aegean. But another interesting thing is not just looking at where the Aegean populations are located in this plane, but also the Aegean fraction. So the Aegean fraction is shown here with a color scheme. And why is that interesting? Is because assuming that some of these galaxies can sometimes switch the Aegean on or off, the Aegean fraction tells us what fraction of the time the Aegean is on, so it's a bit like a duty cycle. And then what you can see here in this case is just, well, it's similar as this, but in fact the duty cycle is higher above the main sequence, even though the bulk of the population here is a bit closer to the main sequence. This is just because we're dividing this distribution by the other distribution in black, which is more strongly peak along the sequence here. As I mentioned previously, briefly, we unfortunately are probably incomplete in terms of finding the low luminosity Aegean in these high star-forming galaxies, so we cannot conclude too much about this. However, what is very robust is what we are very complete at this very high Aegean luminosity, and it's definitely not no Aegean hiding in here. We would have found those ones. Okay, so what I'll show you next is a comparison between these observational results and simulations, except instead of showing you like this in 2D, I will show you trends collapse in the star formation rate direction, in the stellar mass direction, but also as a function of the ratio, so the specific star formation rate. Okay, so the simulations I will compare with are the Magneticum simulations. I don't think we've heard about those ones yet. We've heard about a whole other suite of very interesting and nice ones as well. So they're cosmological, very large volume with baryons. And I'm not going to go through the whole list, but you can actually find all the information on this website, magneticum.org. But relevant for the Aegean analysis, the black hole seed starts at about 10 to the 5 solar masses. It's a kiloparsec resolution. So it's a Bundy accretion rate. And then there's a recipe for thermal Aegean feedback that's already implemented. And there's both kind of a cold mode of accretion and a hot mode of accretion for Aegean. And if you want more details, there's actually a published paper by Michaela Hirschman, 2014. And then there's another paper that will follow on this. Okay, so now to show you the results. So first, the observations again. So for the observations, I'm showing the fraction of galaxies with an Aegean as a function of stellar mass on the left-hand side, star formation rate in the middle, and specific star formation rate on the right-hand side. And then the two colors in blue is the moderate luminosity, 10 to the 43 to 10 to the 45 ergs per second. And in red, the most luminous Aegean, so they're quasars above 10 to the 45 ergs per second. So just looking at the observations, what we can see is that the most striking trend is with star formation rate. So there's a very sharp rise of the likelihood of having an Aegean with star formation rate, and especially sharp at the high luminosity range, but it's also quite convincing here in this intermediate thing. So from the simulation point of view, we get these curves, which have a pretty good agreement. Of course, it's not perfect, and there are some differences, but I think it's very interesting, in particular for the star formation rate panel, that we recovered this very sharp trend between the occurrence of Aegean, so the backload growth, and star formation rate in galaxies. And in all cases, it's a kind of a similar, very broad agreement, and we're right now trying to understand where the differences come from. Okay, so next I'm going to push to slightly higher redshift, going out to redshift 1, which I would say between redshift 1 and 0 is probably the quenching era, because this is when there's a very sharp decline in star formation rate. So there's an important relationship with Aegean. We might still see it there. So in this case, this is going to be a study from far infrared selection. And because the far infrared is probing the dust heated by star formation, so we know that all these galaxies are forming stars. And now the question is, are those galaxies also growing their black holes? So there's a published work back in 2013 from this MIP-70 survey, which we wrote. And now this ongoing work with Herschel, which is much more sensitive at 100 micron. So this is the galaxies on a specific star formation rate versus redshift. The mean sequence is in gray. And you can see that with the new sample, with much more complete on the mean sequence, and we also reach a bit below here. So the idea is just to use all possible ways to find Aegean in these galaxies. So in addition to emission lines that I was mentioning before, we also use X-rays, IRAC colors that tell us about the hot dust, and also radio excess from Aegean. So combining all these together, what we obtain in terms of Aegean fraction versus star formation rate on the left-hand side, or versus specific star formation rate on the right-hand side, is shown here with the points in red for these intermediate redshift galaxies. So there's some open and filled symbols. So the open symbols are the previous published study in 2013, and the filled symbols are this new study with Herschel. But basically, the main result I think that is the most interesting is if you look on the left-hand side, the blue histogram represents the redshift 0 data, and then the red is this now outer redshift 1, and it's basically they're not distinguishable. So this seems to be almost a universal trend where the star formation rate, which is probably just tracing the gas mass in galaxies, it's what seems to be the main predictor to how likely the black hole is growing. So this is like saying there's something fundamental between the gas reservoir and the chance of growing a black hole. On the other hand, for the specific star formation rate, so this is star formation rate per mass, stellar mass, so it's a bit like a gas fraction, so gas mass over stellar mass. It seems that at a higher redshift, there's an increasing likelihood compared to lower redshift here. So this is not so universal across redshift. This seems to be an evolution here. And of course, at low redshift, galaxies tend to have a lower star formation rate. So actually, this blue curve would keep going. I just had to trim it to compare with the high redshift sample. So in terms of the relationship between black holes and galaxies, from this we say that the star formation rate or gas mass seems to be the most closely related trend. So in the last few minutes, I will show you some more subtleties. I would say this is the most global property that we should think about, but in terms of more subtleties and other things. So if I go back again to the specific star formation rate versus redshift plane, and you see the sample from the Herschel sample, these bigger samples now show you where are the X-ray GN. But they're not only X-ray GN, but they're X-ray and unobscured, meaning that we have a very good and unobstructed view of the black hole. So those ones tend to be on the main sequence and a little bit below. But what was very surprising when we first found it in 2013, but now we're just reproducing this result, is that the obscurity GN, meaning that there's some gas between the Aegean activity and our line of sight, is usually thought that this material would be on small scale in a torus around the Aegean. But here we see that there's a relationship because these obscurity GN tend to have a higher specific star formation rate compared to the unobscurity GN. So this is very at odds with this idea of a very basic unification model where the torus is doing the obscuration. So it means that the relationship between black holes and galaxies is a bit more complex because it's not so decoupled. So another way to show these results is if I collapse them along the specific star formation rate normalized to the main sequence, you can see that the black is what the bulk of the sample of galaxies does. So you can very see this clear sequence, this is a clear peak at around the main sequence here. But then the X-ray unobscurity GN and the obscurity GN in blue, we can see how they differ on average in a sense that the absorbed GN tend to have a higher star formation rate per unit mass. So going in a similar direction as this recent work by Marco Cowley here, this is shown from the Z-Forge survey. And this is showing 3 different selection of Aegean, infrared, X-ray, and radio selection. And in each case, it's comparing the specific star formation rate between the Aegean in the solid samples and a control sample of galaxies that are matched in redshift and stellar mass. And you can see for the infrared selection, which can get both obscure and unobscured Aegean, that is actually, again, a difference with so these more likely obscured Aegean have a higher specific star formation rate compared to the control sample, and the difference is not so clear or not so pronounced for the other selections. So this is highlighting what I was telling you. And then the last result I want to show before summarizing is another interesting thing, because so far I've been showing you results about about the global star formation activity in galaxies and the stellar mass in galaxies, but now we're digging into more the details and looking at the morphology of Aegean host. So this is work that's been submitted and it's not yet on the archive, or maybe it was, but in any case, I'll just show you briefly the result here. The idea is to take 2 redshift slices and compare Aegean to a control sample from Cosmos field. So we have a very large area, so more objects. And these are obscured Aegean shown with those red points compared to the control sample in each redshift slice with a gray point. So this is showing the Sursic index versus the radius. And you can see that in both redshift slices, we have a similar result, that the Aegean hosts tend to have a smaller radius and slightly more elevated Sursic index, although they're still not elliptical, they're still disky. They're just these more compact disks. So this is very interesting because it suggests that the Aegean hosts are more compact, and that perhaps this is related to so-called mode of compaction, or that this galaxy, by the compaction, perhaps more gas can go to the center and fill the black hole. So we're not sure this interpretation, but it seems very interesting and intriguing. So now I'll summarize. I think that the question of the black hole galaxy connection is not that simple because it probably depends on several parameters. So namely, I showed at the beginning that it seems to depend on the luminosity of the Aegean, which tells us about the accretion rate. But it also seems to depend on the Aegean obscuration. So this is another thing we have to keep in mind. And then the other thing is that the most luminous Aegean were found to reside in the most strongly star-forming host. So this means that either the Aegean feedback is pretty weak because it's not really shutting down star formation, or otherwise it has to be substantially delayed in the sense that the galaxy is still strongly star forming now, but in the future it will be quenched, but we don't see it yet. I think most likely is that the Aegean feedback most of the time is fairly weak. We seem to be in agreement with the results we heard this morning from the simulation side. But otherwise we also find that if there is one parameter that seems to matter the most in galaxies, it seems to be the star formation rate of the galaxy, which probably traces the gas reservoir. And this seems to be the same out to redshift 1, so the same trend between redshift 0 and out to 1. And then I think we still have to keep in mind galaxy scale processes. And I didn't talk about all of this, but clumpy unstable disk and compact disk and minor, they all seem to have an effect as well. So I think more work needs to be done to really separate and identify the respective roles of these processes. So, thank you.
Questions?
So when you're saying this, it makes me think, I mean, because I remember carrying around a rubric in my head that Hans Walter Rix told me that that when you see a kind of high Eddington rate, accretion rate, which is an X-ray or optically visible Aegean, you're really seeing when there's both an already big supermassive black hole, because it's bright, and then you got a whole bunch of gas right in the middle that's feeding it to give you that high accretion rate and the high luminosity. And this kind of reminds me, oh yeah, when you're seeing these, you're seeing when the black holes are growing, but you're really not seeing when a quenching would happen, because then they wouldn't be shining, right? At some level, the quench things you'd have to see, like you should not ever see at some level a link between quenching, an actual cessation of star formation, and such a high accretion rate. I think it would be very, very hard to see, or it would be a very short time scale that you should see it on. So I think this actually makes a heck of a lot of sense.
Well, I think
what you're finding.
Yeah, well, especially if there could be a slow quenching and a fast quenching, it could mean that the Aegean is more associated with the slow quenching, in fact, and maybe not with such a fast quenching. But I just go back related to your point. This we'll do here. It seems that these lower luminosity Aegean here, I mean, suppose that, okay, we're probably incomplete, but this population is interesting because maybe as the galaxy is quenching, the Aegean itself is quenching too, in the sense that there's less gas to form stars, there's less gas to fuel the black hole as well. You disagree?
Yes, let's talk about that.
Okay, we can talk in the break.
If next speaker can come get ready, and one quick question.
I think your results are very exciting, and they really consistent very well with our thoughts about the blue nugget phase and the compaction. How far in redshift does this conclusion actually is valid? You thought about redshift 0 and redshift 0.7. Do you have results at higher redshifts?
Yeah, so
which of those results are valid?
So the compaction results, they go out to redshift 1.5. So right now, let me. So here the redshift range is 0.5 to 1 and 1 to 1.5. And it becomes harder to do with higher redshift just because it's harder with the morphologies.
No, I talk about the star formation rate above the main sequence.
Oh, I see. Yeah, so the reason we stop at redshift 1 for this other work is to get a range where in the far infrared we're still probing far enough from where the Aegean is going to contaminate. But if we can
to do it at redshift 2?
I think it's possible because we can do the SED decomposition and then try to subtract an Aegean contamination. This was just a more secure redshift range, but we can be more daring and push it. Yes.
All right, let's thank our speaker again.